Going live. All right, we're live. Okay. Just want to make sure there's a delay. I think there's a delay. All right. What's good, party people? Welcome to HackAI 21, where AI can do anything. All right. It is currently 11:04 a.m. So I'm definitely hyped up for this hackathon. If you're as hyped as me or want to be as hyped as me, type hype in the chat in all caps. I want to see how many people are hyped for this hackathon. We're going to get some good stuff, good learning done today. Before we start off, I'm going to go ahead and try to introduce myself. My name is Sanjeev. I am the Vice President of AIS. And I'm going to go pass it off to...
Maitri, yes. Hi guys, my name is Maitri and I'm the president of AIS.
Sweet. All right.
Back to Sanjeev.
We're going to go ahead and go into our next slide.
There you go. All right, everyone. So today, what do we have planned for the opening ceremony? We're going to do a quick introduction to AIS, what HackAI is, how we kind of started. Then we're going to go into talking about our sponsors and as well as the challenges. Then we're going to talk about the prizes that we have for you guys today, and then follow up into judging procedures, review how things are going to work logistically with you guys. Then we're going to quickly review our event schedule. You can find this in the welcome packet, and it'll be on Discord as well with the links, but we're going to go through it again anyways. Then, most importantly, we have a really amazing keynote speech from Dr. Vijay Saraswat, who is the global head of AI R&D at Goldman Sachs. And he's going to be talking to us today about computer science, specifically the AI field, and its impact on the finance industry. And then we'll close up with some final remarks and closing notes. And then you guys will be ready to get hacking. So with that said, who exactly are we? So AIS, the Artificial Intelligence Society, we were founded in 2016 with the mission to promote AI at UTD and in our surrounding communities, and bridge the gap between what people think AI is and what it's really like. We often hear the keywords of like AI and machine learning and all these buzzwords, and it can be hard to kind of learn about what those really are. And so we aim to bring those opportunities to our students, and HackAI is one of the ways that we do this. It's an annual hackathon. The last time we were able to host this was 2018. So we're really excited to bring it back virtually for you guys this year, and bring UTD students, faculty, and guest speakers together to help students learn more about the field. Coming to our sponsors, we are very grateful for the Department of Computer Science and the Center for Applied AI and Machine Learning, both sponsors from UT Dallas, as well as our company sponsors OpenAI, Deep Cognition, and Signapay Deepest.ai. They're the ones who helped make this event possible, and we're very grateful to them. With that said, I'm going to pass it back to Sanjeev to talk about the platforms we've been using today.
All right, bet. So we got two main platforms. You're already on one of them. We got Hopin, and you're on the stage feature right now. So, you know, broadcast to everyone. Everyone can join. There's also two more features called Sessions and Networking. And so Sessions are going to be mainly for, you know, the workshops and the talks that are going to be happening throughout the day. And Networking, I'm going to go explain into our schedule later in this presentation. But networking is going to be really cool if you want to meet other hackers. Small thing on the side, currently our Sessions is a little bit bugged. So if you can't see these sessions on there, just wait until after the opening ceremony. We'll get that fixed immediately. So just bear with us. Now, next, we also have Discord. This is where our socials are going to be happening. This is where you can chat with sponsors if you have any questions. You can also chat with the mentors who are tremendous to help you throughout, you know, building your project, even fixing a small bug, even if you're missing a semicolon. You know, we're good at catching those kind of stuff. So a little bit more about Discord. So you can find general event help with, you know, the guide, and the guide channel is going to basically give you, you know, what the Discord is, what each channel is for, what each voice channel is for, resources, any, you know, maybe what dev post looks like, any resources to help with your project. You know, basically everything you need is going to be in the resource channel. Sponsor subscriptions, I'm going to get those into a little bit more later, but that's basically if you're, you know, if you want to subscribe to a sponsor challenge or basically talk with a specific sponsor, you can just subscribe to that role, and it'll open that channel for you for that specific sponsor. Rules, obviously follow the rules. We're chill people. And then there's obviously a lobby if you just want to, have a general chat with organizers and whatnot. And here's the main part with mentorship. You can basically have two options to contact mentors. You can either go in the Ask Mentors channel, and you can just just throw out some questions, and the first mentor that sees your question will definitely just go ahead and answer you. If you want to have a chat, there's 4 voice channels here, and you can just go hop on a voice channel and have a chat with the mentor if it's something you need to talk about. Or if you're a little bit too shy to ask, in the general channel for mentors, you can go ahead and create a mentor ticket, which is basically a one-on-one conversation with any mentor. The first mentor will just grab your ticket. You have a private conversation with them if you want to ask, any questions you want. So there's 2 ways to contact mentors, so keep that in mind. That's basically it for Discord. We're going to go on to our next slide talking about it's just our Discord and dev post links. We're not there yet. So Discord, if you haven't joined yet, tinyurl.com/HackAI Discord, join there. And then for our dev post, this is also going to be in our resource channel if you for the dev post link, but it's going to be this. If you want to just take a snapshot with your brain, go for it. But we also have those links for you. And everything, by the way, that I'm talking about is going to be in the Hacker Welcome Packet too. So you can follow along if you want to. Let's go on to our next slide. So we're going to talk about some event logistics. So the first thing we're going to talk about is what is HackAI this year about even, all right? Your mission today, all right? You're going to build a software project using artificial intelligence for social good. And you're like, dude, that's so general. Give me some specifics. All right, hold up. I'll give you some specifics. Let's go on to the next slide. So the general challenge, if I had to put it in more descriptive words, is for HackAI, we challenge you hackers to build an AI-based application that has a potential to bring significant positive change at scale to communities around the world. And you're like, oh my God, that's so long, all right? But basically what we wanted you to do is really build a meaningful application and, try to use AI to incorporate it. And there's so many different ways you can do that. And, that's what this hackathon's about, learning those different applications where you can incorporate these skills. So that's our general challenge. Let's go on to some more challenges. So for this, we have the general challenge tracks. All right. So what these tracks is essentially a way, let's say we have a super newbie, right, who's trying to just learn AI, and then we have this god tier AI person who can production scale stuff. It's gonna be a little bit unfair, trying to compete these 2 people against each other. So we decided, why not put everyone in separate tracks? So track 1 is if you're new to AI and ML, this track is completely for you. These are using, existing solutions of code and already built stuff for you, and they're gonna usually involve low or no code solutions. So and then track 2 is going to be, if you worked with AI before, but haven't dived too deep, then definitely go for this track. And, these are going to be using also pre-existing frameworks and data sets on top of that. And track 3, like I said, these are your top tier people. If you know your AI in and out, this is going to reflect your experience to implement high novelty solutions. So this way, based on what track you go in, it's going to be, you're only going to compete with people who are on the same track as you. All right. So that's how we're splitting our general challenge. General challenge is the same for everyone. It's just the project complexity of your project you submit into whatever track fits. All right. We're going to go on to the next one, talking about our sponsor challenges. So first, we have OpenAI here, and let's get a brief description about what OpenAI is. So they're an AI research and deployment company, and their mission, just like kind of the hackathon theme today, is benefit all of humanity with artificial intelligence. 9 months ago, they released the first commercial product called the OpenAI API. And by the way, you guys should have gotten emails yesterday about that. So if you haven't set up your OpenAI account yet, go ahead and do that. There's going to be a workshop today on how to use the the API. So definitely do that. And if you have any questions, definitely we're gonna have a channel on the Discord for OpenAI, so you can ask them there. And for job opportunities, check out openai.com/jobs. And their challenge for today is going to be design a system using OpenAI's API and AI techniques to help with hospital administration. Another social good challenge. All right, let's go to our next sponsor challenge. We have Deep Cognition, and so we have a video for them just to kind of explain what's up with them.
Hi, my name is Kate Curtin. I am the marketing director at Deep Cognition. Deep Cognition is an artificial intelligence platform and solution provider based out of Dallas, Texas. We are a startup that began in 2017. Primarily, we focus on solutions, but we also have what's called Deep Learning Studio. Deep Learning Studio is a development platform that is typically used by researchers, developers, or really anyone who's trying to build a module at an increased rate and not having to use coding. So Deep Learning Studio allows you to build models inside of our platform as well as deploy them directly from Deep Learning Studio. Today in Hackathon, you're going to be using Deep Learning Studio to build a model that promotes environmental stability. If you do have any questions, feel free to reach out to us directly, as well as if you are graduating in the next year or so, if you are looking for an internship in AI, machine learning, feel free to email me your resume and we can set up a conversation as far as what that internship would look like. Typically, it's about 3 months, and you would work with our engineering team to develop models as well as content for our users. I will share my email with Gary, so if you do want to email your resume or if you do have any questions, please feel free to reach out. Again, thank you so much for participating in Hackathon, and we wish you the best of luck. Thank you.
All right. So basically, their challenge is going to be utilizing Deep Learning Studio, which is the tool. In terms of downloading it, we're going to have a little bit of instructions later in the hackathon. And so you can download it. It's just a simple installation for the tool, and it's a graphical interface for building, machine learning models. So it's really, really cool. Definitely check this challenge out. And their challenge is basically developing an application that promotes environmental sustainability. All right. So it's a really large topic, but you could probably think of some few ideas of what would fall under this category. Let's go on to our final challenge, sponsor challenge. And we're going to go ahead and click this video.
Everyone, I'm Chaitanya from SignaPay and DeepRisk. So SignaPay is a payments company, and DeepRisk is a startup we've spun out of SignaPay. So DeepRisk focuses on providing risk management to banks using a machine learning platform. And I'm very excited to see all kinds of cool solutions that everyone comes up with during this hackathon using the latest and greatest tools in AI. And yeah, looking forward to see the hackathon and see how I can interact and learn from you and help you out in your future endeavors. Thank you so much. Bye.
All right, so that was Chaitanya from SignaPay and DeepRisk.ai. And so his challenge for you guys today is going to be creating an application/model that's going to impact or help businesses. All right, so just kind of think that, just make it in your brain, just think of what kind of applications they can do there. All right, we're gonna go on to our next slide. And by the way, just kind of sum things up. So we got the AI general challenge, and then we got the sponsor challenges. So everyone's admitted to the general challenge, but you can also opt in to do the sponsor challenges if you like. That's just a little side note out there for you guys. We're gonna go and pass off to my three.
All right, so coming to prizes, as Sanjeev mentioned, we have the general challenges and we have 3 different tracks. So the way that we're doing prizes is the best overall winner. That is the best project, the highest scoring one, in quote. That team is going to be getting an Apple AirPods Pro for each member. The best of track 3 prize is a Powerbeats wireless headphone set. Best of track 2 is a Polaroid instant camera. And for best of track 1, we have an Amazon Echo Dot. Then going into our sponsor-specific prizes. So these are prizes provided by the sponsors themselves. OpenAI is giving out specific OpenAI API credits, so more details in the welcome packet for that. Deep Cognition is providing 1-year subscription to Deep Learning Studio Pro. Great opportunity to keep building AI projects even after HackAI. And for SignaPay, we'll be providing a Rocketbook Smart Notebook. Some really cool prizes to set your sights towards. And as I mentioned earlier, regardless of team size, every team member will be getting these prizes. With that, so coming to judging, and we'll go into the schedule in a little bit, but basically once hacking ends at 12 p.m., the hacking period is going to be completely over. Judging is going to take place between 1 to 3 p.m. Central Time on Sunday. So basically what's going to happen is between 12 and 1 p.m., once we have all the projects on DevPost, what the HackAI organizing team is going to do is we're going to pull all those projects and assign each project a specific table number in quote. Basically, it would be the same thing as if this was a real in-person hackathon. And you have judges like coming to your tables and you present to them and talk to them. Basically, we're doing the exact same thing, but virtually instead. So once you get your table number, in the announcements channel, sometime between 12 and 1 p.m., you'll be able to see what number your project got. And then on Discord, on like the left side where you have all the channels, we're going to have a specific voice channel for each project table number. So all you have to do is go into that voice channel when it's time to begin judging and wait for your judges. So you're probably going to have multiple. A judge is going to come in, you're going to be able to share your screen on Discord, talk to them, present your project. They might ask you some questions, give you feedback, and once that's done, they'll be able to score from their end and they'll leave, and another judge will come, same thing, process will repeat until 3 p.m. You will have about 2 to 4 minutes to present your project, so we recommend that you keep it short and sweet, basically just cover all the basics. Again, there's more details in the welcome packet as well. If you have any questions about dev post, about judging process, anything along those lines, you can always ask organizers to help you. And at the end, at 3 p.m., we'll compile all the scores to announce winners at the end. And if there's a tie for any of the awards, we will let the tie teams know, and we'll do a rejudging and then announce winners during the closing ceremony at 4 p.m. So that's basically a rundown of how judging is going to go. And I'm going to hand it back to Sanjeev to talk about our schedule for the day.
All right. So these are just some really important deadlines. Just keep in mind. So definitely pay attention if you haven't been paying attention at all. So hacking begins at 12 p.m. All right. So basically, essentially, kind of after this opening ceremony, hacking is going to bend. So 12 p.m. Keep that in mind. 2, project submissions are due at 11 a.m. on Sunday, March 28th. So basically, tomorrow at 11 a.m. project submissions are due, and I'll explain this deadline a little bit later. So hacking ends at 12 p.m. tomorrow. Judging begins at 1 p.m. and closing ceremony at 4. All right. So the difference why project submissions and hacking are, kind of different, not due at the same time, is because, if we have your project submissions and, your project name is there, your team name is there, you got a general description of your project, we can go ahead, like Maithri said, you have to assign you a table number, right? So if your project's already in online, we can just pull out, the project name and assign that project name a table number and then release it, around between 12 and 1. So it gives us organizers time to just kind of organize and make sure you guys are good to go for judging. So that's why we just need your project submissions at 11 a.m. Hacking ends at 12. So you can still, code up something if you got that 1 hour time if you need it. So these are the 5 main important deadlines. So keep these in mind for sure. All right, let's go on and talk about a little bit about our schedule now. So today, 10 a.m. was check-in. So check-in happens on Discord. If you've registered and got accepted, right, you got acceptance email, whatnot, then your check-in should have happened smoothly for you. There's a little bit few here and hiccups there, but check-in, you can still do it if you haven't. Opening ceremony, we're in it right now. Team building, networking. So this is what I was talking about a little bit earlier. So, if you still haven't found a team and you think like, hey, I'm, texting, try to find a team through text is not really my thing. I want to kind of meet people face to face. From 12 to 1, there's a networking feature on the side. So you should be able to see, like right on the left side, there's networking. So 12 p.m., it opens up. You can just join in and you're going to be matched with a random hacker. You get 30 seconds to 3 minutes to just talk with a hacker, see what your interests are. If you guys think you're a good fit for a team, then just team up, create a Discord group DM, whatever you want, all that jazz. At 1 p.m., we have the Open AI workshop. 2 p.m., we have Deep Cognition workshop and also an AIS workshop on deploying a model to GCP, which is Google Cloud Platform. 3 p.m. is we have Neural Nets with Curious workshop, and we also have a SignaPay/DeepRisk talk. 4:15, we have Alexa Social Bot Challenge presentation by Kinjo Basu. That's really cool. At 5:30, we also have another talk about AI and its application industry. So maybe this guys can help you a little bit ideate for project ideas. At 7, 9:30, and 11 p.m., we have our socials. So, if you feel exhausted after, grinding for 6 hours, just want to chill out with the organizers, chill out with the gang, just hop on these socials. We'll definitely have some fun and, be great meeting you guys for sure. So let's go on to day 2. And day 2, we don't have too much. So like I said, 11 a.m. submissions are due on DevPost. 12 p.m. hacking ends, like I said. And 1 p.m. is going to be general track-based judging. And like Maithri said, it's going to be for 2 hours so that everyone can be, equally judged, have, good amount of judges see their project. And then 4 p.m. we're going to have our closing ceremony. All right, so that's basically it for schedule. I'm going to probably pass it off to my three.
Yes, awesome. Thank you, Sanjeev. So now moving on to part that I'm most excited about, our keynote speech. We are extremely honored today to have with us Dr. Vijay Saraswat. Dr. Vijay Saraswat is the Managing Director and Global Head of AI Research and Development at Goldman Sachs. He earned his BTech in Electrical Engineering from IIT Kanpur in 1982, and he earned his Master's and PhD in Computer Science from Carnegie Mellon in 1985 and 1989, respectively. Dr. Sarsworth has published more than 100 papers, collaborated with more than 100 researchers across logic, concurrency, programming languages, and AI. He received the 1989 ACM Doctoral Dissertation Award for his work on concurrent constraint programming and the 10-year retrospective 2005 Most Influential OOPSLA Best Paper Award for his team's work on the XGen programming language. Currently at Goldman Sachs, Dr. Sarsworth leads a team of researchers and engineers building knowledge extraction, representation, and reasoning frameworks for the firm. He joined in 2017 and was named Managing Director in 2019. And in his 30-plus years of research career, Dr. Sarsworth has been a member of the research staff at the Xerox Palo Alto Research Center, AT&T Research Center, and the IBM T.J. Watson Research Center. We're really, really excited to hear about his work and experiences today, and this will be a really interactive presentation. So if you have any questions while Dr. Sarsworth is presenting, you can feel free to type them in the Hopin Stage chat that you'll be seeing on your screen. And with that said, thank you again, Dr. Sarsworth, for joining us today and taking out your time. I'm going to go ahead and hand it off to you. So I'm going to go and stop sharing my screen and hand it off.
Awesome. Can I share my screen now?
Yeah, go for it.
Mm-hmm. Yes, you should be able
to. Yeah, let's do the entire screen. Excellent. All right, folks, do you see my slides now?
Yes, we can see them.
Yes.
Excellent. Let's go back on. All right, it's my pleasure to give this talk. It was rather a quick development. Earlier in the week, I was speaking with Gopal Gupta, and he suggested that this might be a venue to talk about some of the work that we are doing, particularly since the company I work for now, Goldman Sachs, has opened an office recently in Dallas. And I believe a number of students are from UT Dallas are already engaged with Ram Narayanan and the folks at the GS office in Dallas. So today what I'm going to speak about is, in fact, this remarkable era that we are in computer science. Most of you are here because you're already jacked, and your presenter just now made sure that you were jacked. He was jacked and ready to go. I am as well. Not just for this event, but for the big era that we are in computer science with the advent of machine learning techniques. In fact, in my opinion, this era, the advent of deep learning and the impact that it is having across computer science is probably comparable, if you go look back the last 40 years, 50 years or so, mostly to the emergence of high-level programming languages on top of the stored program computer. It's that massive a change. So you guys were just starting out in computer science and in AI. This is an amazing time for you to get up to speed with the ideas that will have a very, very big impact over many, many years to come. So what I want to do is, mostly people talk AI ML, and they forget that this is embedded in a far larger and far more sophisticated environment, computer science, that's been with us, as I said, for about, this is 2021. So it's been with us for about 60 years at this point. And it has pervaded every aspect of life, as you guys are very well aware. So I don't want to separate these two. Rather, I want to talk about how, instead of thinking about working on AI applications, what you should really be thinking about is how can you apply the new ideas that are coming to the forefront now in every aspect of computer science. And by this, I mean in databases, database optimization, programming language, of course, programming language design, debugging, testing, the reinforcement learning techniques stuff I'll speak about now, which in fact are quite applicable in the arena of debugging software. This is unfortunately a really short, I was asked to give a really short talk. So I will keep my remarks brief and answer comments, questions coming in on the side from the channel. But let me simply say that a ton of amazing stuff is going on in the physical sciences, in computational chemistry, in quantum chemistry, using deep learning ideas to solve the Schrodinger equation. Some of you guys may have heard of, fundamental equations of physics, solve them in a much more powerful context than was possible before. So deep learning isn't really just about face recognition and stuff like this. It has much broader, the underlying ideas have much broader ramifications. So my purpose in the next 10 minutes or so is to give you a little bit of sense for what is this underlying significant shift and how we can make it in such a way that we don't forget all of the computer science that that's built up the world around us today, but we're able to enhance and extend that stuff. All right, so a quick sketch of 1.0 is what I call, the work in computer science up till around 2016 or so, when to folks like me who are in the research world, it became completely clear that deep learning was here in vision. There were remarkable results that could not be accomplished anywhere else. And the real question was, will this work in other domains? And the holy grail that was put forward at that point was, hey, will this make a significant difference in natural language understanding? Natural language is by far one of some of the most complicated stuff that humans deal with, not just at the level of perception and low-level understanding, but at the level of deliberative, reflective thinking, theory construction, formation, so on. All those are built on the human facility for communicating in a language. And so the central question was, will these techniques work in a far more, to several of us, far more sophisticated contexts such as natural language? And that, in fact, has come to pass, I would say, in 2020 is, in my opinion, the watershed year where it also became completely clear that deep learning has transformed the natural language space. And in fact, the work of OpenAI is, OpenAI has made significant, one of your sponsors has made significant contributions to this space as well. So, before we come to the story after 2016, let me just go back and talk about how we used to do things. Well, it was pretty simple. You finally had a machine that could actually do what you wanted to. The downside was it did exactly what you asked it to do. It didn't do what you wanted it to do. You had to tell it what to do, and it did exactly that and nothing else. So in other words, what the whole framework of computer science till 2016 or so was very, very good at was around understanding how to specify solutions to how to provide solutions to very well specified problems. The input data is clear, the output transformation, the output data you want is clear, you have an idea of an algorithm for the underlying transformation. Now the question is, how do you implement this? How do you debug it? How do you test it? What sort of programming language should you use for it? Is there, computer science notions of, is there concurrency involved? How much memory do I have? Do I have to optimize this? Is it a square algorithm? It's an exponential algorithm. All those sorts of things were the central concerns for this entire era. Some of the things that I just mentioned show up in the development of logic and logic-based frameworks for doing not just programs that talk about the world, the domain of AI, logic and AI, but also logic in computer science, proving your programs correct. This is actually a really big deal, by the way, even in the domain that I work in finance. In a context of, let me just put it out there, trading software. You are writing software that has to run at very, very high speeds. It's got to respond at the level of microseconds to incoming buy and sell requests. It's got to match that up. And now you can't just hack your way into writing this code, because at the end of the day, this software is going to deal with a huge amount of money flowing through the system. And there are people who care that this code does what you said it would. You said it's not going to, favor my uncle. You said that if an order comes in before another order, then that order will be dealt with before this order. There are priority relationships. And not just you said that to your customers, the SEC said you're going to have to follow certain rules. So now the challenge that you face is you're going to write all of this very, very high performing code. And if you don't get it right, someone could sue you or the SEC could fine you. These things have happened. So correctness and things like that remain even in this modern age with all of the, hype around working with machine learning techniques. This still remains a pretty central thing that we need to work with. Two big ideas coming out of that time that will carry over to this new era. The transformational reactive stuff is just a way of understanding things, and sketching. So let me get to these. So I don't know if you folks at UT Dallas, the computer science framework there emphasizes these ideas of transformational versus reactive. Transformational is the usual stuff. You write a sorting routine. You write something to take an input, transform it to get an output. You run the code once, the code on a given input, you run it once, you get an answer, you're done. Reactive computing, which was founded by Harel and Berry and a whole bunch of folks in the 80s, has to do with maintaining an ongoing, persistent interaction with the world. Classic example of controllers. You're going to fly a helicopter on Mars. How the heck are you going to do that if you don't actually have software that knows how to maintain the right speeds, the attitude of the helicopter, and so on, autonomously? So that's stuff that is going to interact with the environment, with signals received from the environment, and provide the controls so that the right control regime can be maintained by the instrument. The languages involved, the concepts, the programming frameworks, how you prove this correct are very, very different from the transformational framework. The reason I bring this up is because these ideas, in fact, have a direct analog in the context of machine learning. But before I go that, let me speak a little bit to the central idea that will show up in the machine learning context as well. And this is the idea that, it's sometimes not so hard, even if you know the algorithm, to be forced to write precisely each and every bit and get it correct. I know I get off by one errors all the time in my loops. So Armando Solar Lezama did his PhD in the space of sketching, program sketching, back around 2007, 2008 at Berkeley. He worked with me for a bunch of years on this. We did a ton of papers together. He's a professor now at MIT, developing with a large group, continuing to develop these ideas, and in fact now in the context of machine learning as well. And the central idea here is, instead of doing program synthesis the old-fashioned way, you give a piece of logic and you ask some theorem prover to produce the piece of code. We are actually going to provide a piece of code with holes in it. These question marks are holes. And we may provide some other information about what this piece of code is supposed to do, such as input-output behavior. Say on this input, it's supposed to produce this output. Maybe give a dozen examples of that kind. Maybe say things like, hey, this should not throw any exceptions in the language of the exceptions. So what Armando said, set of techniques for generating code based on various artifacts that get provided. So think of it as a very high-level compiler. Your programming language now has notions of question marks. And what it does is, instead of just generating code in machine language, it can also generate some code in the programming language you're working in to fill in these question marks and satisfy the considerations that you laid out ahead of time. These ideas, sketching ideas in particular, carry over to our new world. So what is our new world? A simple way of looking at our new world is this. What if you don't know how to write the code? Now, of course, I should preface this by, we are living on top of another 20, 30 years of Moore's law. So if I had said something like this back in 1990, and people actually did, it simply was not practical. It was still these ideas, this notion that we could have a computer perform tasks for which we can't actually write down the code. That's the essence of AI ideas. These ideas were still very much gleams in people's eyes. Jeff Hinton, one of the fathers of deep learning, was in fact a professor at CMU. When I was a graduate student there, the backprop algorithm was developed when he was at CMU at that time. And it's really taken 30 years of work by Jeff Hinton, Jan LeCun, Benjo, Schmidhuber, and other pioneers in deep learning to take those simple ideas and get them now to a place where you've got a robust framework you can apply in many different areas. So what's an example of a problem you want to solve, but you don't know how to write the code for it? The software is going to be given a piece of given a picture, something like what you see on the left-hand side, and it is supposed to come up with a label for, on the top left, people, top right, child, house, study, and so on. Now, of course, understand just the mind-boggling, if you come at it from a logic point of view, the mind-boggling amount of inference that is going on in a code that can actually do this labeling. Is that stuff on the bottom left a house? It could be tons of other things. Humans understand that some sort of construct like that thing is a building. It's designed in such a way that humans should live inside it. Okay, the generic word for that is a house. So I'll call it a house. I will not call it a shed. It's not a barn. It's not a place where animals live. It's quite likely a place where humans live. These sorts of distinctions, we need our code to be able to make these distinctions. Most importantly, it needs to take any image and produce a labeling for it that a human looking at it would say, yep, that's right, that makes sense. You're going to have to deal now in a very, very different context. You deal with data that is noisy. Instead of your algorithm getting an array of numbers and you needing to sort it, very precise numbers, that's 2, this is 5. It's not, some fuzzy representation of a number. Instead of that, you have to deal with noise. You have to deal with uncertainty. Is this picture really the picture of a child? Or possibly it's a picture of a parent holding their child? There are different possible things. You're not quite sure how to label this properly. And you have to deal with very high dimensional data. This is a little bit hard to communicate in a very abstract, high-level talk. But simply think about it like this. How many independent pieces of information would you need to specify to unambiguously identify your data item? In the case of these pictures you are seeing, we are talking of tens of thousands, hundreds of thousands of features. So that's high dimensional as opposed to 3, 4, 5 dimensions. So the central task now becomes, we move the underlying mathematics, the underlying way that we think about computer science, away from discrete math, well-specified entities, which can be in precise links with each other, such as a pointer from this piece of data structure to another. We move away from that precision, which, by the way, has been enormously valuable for us. Move away from that to also now deal with noisy data, uncertain data, high-dimensional data. From the viewpoint of underlying mathematics, we have to move to what people have been studying, mathematicians for centuries, the arena of real numbers, of limits of continuous functions over real numbers, of differential equations, of analysis, and so on and so forth. And now the challenge becomes this. What we want to do is write a piece of code which will have a huge number of holes in it, like the sketching stuff I mentioned. And what we're looking for is an algorithm which, given some examples of input-output behavior, just like the sketching world, will actually be able to figure out what these holes are and fill them in. This is, the idea is very simple. It took these 30 years of work by so many interesting people to actually evolve a sophisticated methodology for dealing with this in substantial generality. And that is the arena of deep representations and deep learning. The essential idea here is that this algorithm, I'm going to come to it in a minute, the workhorse of this space is stochastic gradient descent. This algorithm is actually knows to do just one thing. We are going to formulate our problem as a problem of finding an approximation to a function in some high-dimensional space. And this algorithm is we are going to provide it with a space of possible functions. That's what the parameterization is going to do. You choose different values of the parameters, you'll get a different function. So by leaving these holes, we are specifying a family of possible functions. And the purpose of this algorithm is to find amongst a possibly immense, and I really mean immense, trillions of these functions, a function which satisfies the input-output requirements that are given to you in a reasonably good way. So this central idea that we now move from describing functions to a space where algorithms code is going to determine an approximation to the function that we specify with some other artifacts like input-output pairs. This is the framework that we live in. The central breakthrough here idea was around, back at the time of Minsky and Papert, that one could use the so-called artificial neurons, very, very simple compute elements that were motivated for some researchers through their approximate understanding of how neurons work in the human brain. But the idea, I think of it as it's like a transistor in the old way of wiring up computers. It's a simple universal compute element, and you can put a whole bunch of these elements together, wire them up in particular ways, and you have a universal approximation theorem that says that any function that satisfies certain properties, but very, very general properties, can be approximated by a function written in this style using these elements, these neural elements. So the deep learning idea goes beyond that. It goes beyond saying we're just going to take a bunch of these neurons. It further goes to the idea of, in fact, it is important that these be organized in layers. And this is where the deep comes from. And the point about these layers, you can see on the left-hand side schematically described, is that if you set this up properly, you can, in fact, arrange things in such a way that these layers are learning abstractions that are relevant to compactly describing this function. So in the context of faces, it's amazing. If you go look at I've got a bunch of references in my slides, so you can go look at them. You may already be very, very familiar with how these things work. Any case, what you see is at the bottommost layer, you pick up things like edges, and then you start to pick up slightly more complex features. And ultimately, you end up with features which are, in fact, not dissimilar to the features that a human would recognize in images like this. So from the viewpoint of logic-based representations, where you had very discrete representations, we now move to a very so-called distributed representation, where a concept might in fact get presented via the specific weights, the specific interactions between a large number of compute elements. You cannot localize a concept in one particular place in your neural network. That said, there has been some amazing recent work, again from OpenAI, that speaks to this idea that actually there can be neurons trained in an appropriate fashion. You might end up with some very key neurons that in fact are wired to certain concepts, even in a multimodal context. You've been training with pictures, you've been training with text. And in all of that, there's a neuron that will fire when you present the text corresponding to the concept, or when you present a picture corresponding to the concept. Fascinating, fascinating stuff. So I don't have too much time, so I'm going to skip over this quickly. You will learn a lot about it if you have not. Here is the amazing thing, deep thing to go away with. What is really the power behind these new representations is that they scale. This word scale gets used heavily. Let me say what it means. So back in the early 90s at Xerox PARC, I worked with some colleagues on building out a model for a photocopier. People are going, photocopiers jam. You need to repair them. You're going to have to develop training manuals for it. How are you going to do it? Well, Johan de Cleer, in whose group I was working, had this idea, model-based reasoning. We are going to construct a logical model of this complex real-time controlled device, both its physical behavior as well as its control system. That will enable us to do a whole bunch of algorithms, like diagnostic algorithms, developed from this model. Fantastic. We worked on it. Highly interesting, very challenging. It took us a couple of years. We got great stuff done. Guess what? Doesn't scale. You need 3, 4, 5 PhDs to do something as simple and constrained as this. If you want to understand all the information in all the books in the world, These techniques are not going to scale. What scales here is this kind of computation, where these functions that I spoke about are functions that you can approximate even if these functions are over extremely high dimensional spaces. This used to be the curse of dimensionality, used to be a major impediment to a whole bunch of algorithms ranging from dynamic programming and so on, large class of problems. Now it turns out for certain sorts of problems, neural networks are able, you can set up your architecture in such a way, you can train in such a way that you can find an approximation to a function which performs really well for you. This is the amazing stuff. 1.6 trillion parameters. We already have language models now that are at 175 billion parameters. And there are results now about people who have developed code problems for which networks scale up to such massive numbers. That kind of scaling is what is completely transforming our world today. I will, Maitri, how much time do I have? Another couple of minutes?
You have some time, Dr. Saraswat. We have like about 10 minutes left. So
let me take 5 more minutes then.
No
Let me speak to now some of the work that's going on in my lab, building on this amazing work from Google, OpenAI, tons of researchers, Facebook, Microsoft, and so on in the natural language space. That's one of the remarkable things about machine learning. It's not just the ideas, it's also the ecosystem, how open folks are about sharing data sets and sharing code. That is really what has accelerated the breakthroughs that you see here. On the left-hand side is a picture taken from a particular kind of a neural network, the attention-based network that came out about 3 years ago, and is the basis for remarkable improvements in a large number of tasks in natural language. Again, I apologize, I don't have time to go into a ton of details. The central thing that you face here in natural language is you've got a sequence of text words. Now, the meaning of these words often depends upon the meaning of the other words in that sequence. So the meaning of other words in that sequence, in that context, which could go back a fair bit. So now the challenge is when you're going to train a neural network to extract the meaning, much like you saw the extraction of high-level patterns for visual images. Here we're talking about high-level patterns in the space of meanings, which I've not told you what meanings are. That's another really complicated topic. But just imagine that there is some mathematical space of meanings and you're looking for patterns in those spaces. And you're looking to, in fact, find function approximations that will take from, that will go from your input sequence of tokens, actually, the cat jumped over the hot roof, stuff like that, into some representation from which you can make inferences, conclude other things that need to get said, and things like that. So the central challenge is to build up a representation of this context in a way that it is sensitive to the other words in it. From a neural network, the way I described it to you, there isn't enough structure. People, of course, knew this a very long time ago, came out with recurrent neural networks, LSTMs, things that actually know how to take advantage of the sequential nature of the input. By sequential, I mean one after the other. There is an order, and that order is semantically important. In a picture, in an image, there is no order at some level. All those bits get presented to you instantaneously. Again, I don't have time. There's so many amazing ideas here. Let me just say, the way in which we program today, prior computer science 1.0, is by figuring out properties of our algorithms and by embedding them in our code. Now what you got to think about are the symmetries of your data and how you go one level indirect and how you set up your architecture. So within that architecture, this algorithm, SGD, can work indirectly with the data to produce the parameterization that you need. I realize I'm almost talking like poetry here, but these are actually meaningful ideas. The big point here is that there are symmetries, and those symmetries need to get represented in the structure of your network, so that the task of finding that function is simplified. You don't have to train with an immense amount of data. You don't have to take a huge amount of time. You can actually train with much smaller amount of data and get very reasonable approximations. This was the insight in the Attention is All You Need paper, the idea that look sequential stuff, but in fact, instead of going left to right in sequence or right to left in sequence or both together, it's much more important for us to set this up in such a way that some buffer of text is available all at once. And we can simultaneously operate on pairwise interactions across all of these. Turns out the roots of this idea in linguistics have been around since the 80s. This is how LFG, a major framework that I worked on for traditional 1.0, traditional natural language understanding, that's how it works. No separation of layers between syntax and morphology and semantic constraints. You work all simultaneously, all across possible pairs of interactions between them. So it's wonderful to see a neural architecture which at some conceptual level has the same idea be responsible for some of the breakthroughs that we see today. To give you a very concrete idea, this has all been very abstract and high level. I'll now point you to very, very concrete stuff. So I work at Goldman Sachs. You would have heard of Goldman Sachs as a bank, and it does amazing amount of stuff in the financial world. But from my very low-level computer science points of view, what is it? It's an industry that runs on documents. I picked this up when I was at Xerox PARC. John Seeley Brown, the head of PARC, in fact, was instrumental in repositioning Xerox Corporation as the document company. And now I see documents everywhere. Why are these documents such an important part? The financial industry, what happens? You establish contracts with other counterparties. On the basis of those contracts, you're going to trade, hundreds of millions of dollars. Those contracts better be very clear, very crisp about legal consequences of all sorts of things under all kinds of edge conditions. And these documents are pervasive. If this is a loan document, if you are Facebook and you go to a bank and you say, give me $1 billion because I have to build up a data center in the Dallas, right? You'll get that $1 billion, but more importantly, you're going to get a 300-page PDF document that has a whole bunch of constraints written out in legalese around what you, Facebook, can do or cannot do in the future, as long as you need to be in good standing with respect to this loan. So you'll get your $1 billion with 300 pages of PDF strings attached to it. So clearly, it becomes enormously valuable to the corporate that wants the loan, to the banks that are issuing these loans, if you have code that understands the structure of these 300 pages. And that's just one example. There are literally hundreds of types of documents that the financial industry runs on, and getting code to understand these would cause a major transformation in the space. Bunches of almost every aspect of a bank touches documents, and they're professionals, highly trained professionals who know how to look at these complex documents and extract the information that is appropriate for the task at hand. And that is what we aspire our code to be able to do based on these natural language understanding techniques and the breakthroughs that I've just spoken about. Let me quickly give you a whole bunch of concrete examples. Tasks on the left, these are, by the way, not tasks that today you will find in the major natural language conferences. So unfortunately, the agenda in natural language understanding in the major conferences has been driven far more by, let us say, the consumer companies, far more by need to understand, text out on the internet or text in Twitter, tweet feeds, and so on and so forth, much less by the need to understand professional text the way that professional humans would. There are a lot of significant challenges in this kind of professional NLU, but that's our area of focus. That's what we're working on. I'll give you a very simple example. Here, on the left-hand side is a paragraph taken from a loan document of the kind that I spoke about. And guess what? If you look at this, squint at this hard enough, what do you see? It's Python. It's a formula in Python written by a lawyer in rigorous English that will stand up in court. On the right-hand side is what I really want to extract from it so that my software can get this executable representation of this complex 300-page document, and I can plug numbers in that correspond to the current LIBOR rate or whatever, and I can find out, according to this agreement, what should the rates be, how much margin there is for this to go up before some other clause get triggered, etc., etc. This remains a hard challenge. We have worked in this space, which we made some progress. We've got stuff working, but there are a lot more challenges like this that lie forward. There's a whole bunch of stuff don't have time to go into, just around reactive learning, and in fact, the importance. This is where the reactive stuff that I talked about, reinforcement learning, the reactive framework I talked about, comes into play. Interaction between the world and the agent and maintaining it. Now the big deal is that the agent can contain a learning submodule that is figuring out patterns. Again, same approximation ideas from deep neural networks, function approximation ideas. It can figure out patterns in these interactions, particularly given a reward signal that comes in from the world, and learn how to optimize that reward function. There are papers out there now showing the importance of these ideas in the context of finance, particularly in the context of automated trading and market making and portfolio optimization and pricing of derivatives. Complex stuff that has been dealt with, and I think this is where I will stop, has been dealt with in the past. Remember the remark I made about scaling, has been dealt with in the past by really amazing people like Myron Black, like Scholz, folks who got Nobel Prizes for their invention of their understanding of the underlying mathematics and its formulation in the form of stochastic partial differential equations for predicting the values of derivatives built on some underliers. That's where it used to be. Now, with these data-centric ideas, we are actually in a position where we can investigate, let me call it synthetic mathematics or synthesized mathematics. We can actually investigate pieces of code that will learn patterns from massive amounts of data in the financial market, in other markets, and construct effective empirical mathematics on the basis of which you can make predictions. Might not be easy and simple and neat and tied up in a bow. On one page, you can describe, this is the stochastic differential equation, these are the constraints. Might not be that. But empirically, it's going to be a whole bunch of weights in a messy neural network. But based on that trained system, you can now go take action, make predictions and take action in a way that's with great fidelity to the data in a way that was unthinkable before. Fantastic time. I'm going to stop. The questions, I'll take them. I have put out here on this last slide, if you are young guys, you might be getting very cocky. I'm going to go solve the world. Just understand these are amazing transformations. They really are at the heart of a bunch of new things we can do, but we are far removed from being able to do what humans can do. And this layer, this cake is supposed to show you outer concentric layers. When we get to what I call the Ruth Bader Ginsburg test, and I used to call it, even before she passed away. When we get to AI that can solve the Ruth Bader Ginsburg test, then I'll know we've done something remarkable. And that test is simply, you've got to be able to listen to all the arguments made in a particular case in front of the Supreme Court and render judgment, you meaning this piece of code, render judgment, meaning produce a written opinion, which is of high enough quality that the other judges in the Supreme Court cannot figure out whether code did it or a human did it. The reason this is so important is because in this country, meaning, we talk about natural language understanding, about understanding the meaning of words in text. The question is, who makes those meanings? And ultimately, in the legal context, meaning is made in this country, in its political system, by the judges in the Supreme Court of the United States. They are not just interpreting, they are making meaning. They make new phrases and have them take specific meanings. Like in the context of free speech, there are a whole bunch of carve-outs. True threat is a simple, innocuous-looking English phrase. It means something very precise in jurisprudence, thanks to a series of judgments that came out from the Supreme Court. So the notion of a piece of code that deeply understands not just text, but the world, the political economic world, the American way of life, and is able to write out in that context a judgment that makes meaning, we are far removed from it. Thank you. I'll take questions.
Thank you so much, Dr. Saraswat. I think we do have a couple of questions in the stage chat, if you can see them, but I'll read them aloud anyways. Yeah. Dr. Gupta asks two questions, but first being, if you could speak to the explainability that has been an issue raised about machine learning.
Yeah.
And second, if Goldman Sachs is using any tools today based on machine learning.
Yeah, of course, we're using tons of tools. I can't really get into specifics. Let me simply say this area that I spoke about of deep document understanding, which my team works in. We have a number of fielded applications. These operate on top of a variety of deep neural networks, BERT-style stuff, various other architectures we have devised on top of that to better fit these tasks that I spoke about very, very briefly. Yeah. Chaitanya Vaidya, can I answer? Let me just pick up some of these questions. So Chaitanya, I'm very excited about some recent work on neural ODEs, and neural SDEs, neural jump equations and stuff like this. So here is where I come from, and Gopal will, can speak a lot more to this background that I'm speaking about. I come from the world of logic, from the world of understanding the world around us using some pretty high-level tools. And mathematicians, as I said, over the last centuries have worked in the arena of real-time analysis and developed differential equations and the like. And then we work with neural networks. This is like, and now you're going to work with transistors. When you've got chips in your laptop that have billions of transistors, and you want us to start going back and thinking in terms of these low-level compute elements, the neuron, it makes no sense. Of course, neurons scale. I can get 1.6 trillion neurons. That's huge. But there's got to be a way, one would think, old people like me think, there's got to be a way where we can develop new programming paradigms on top of this substrate of neural networks, which speak to a much more higher level way of dealing with the world. And so this breakthrough a couple of years ago by David Dovenou and a bunch of his colleagues, there are many others involved now, out of University of Toronto, is around, hey, it turns out we can actually combine ODE solvers, ordinary differential equation solvers, with neural nets in a single network, if you will. So it turns out, like many of these ideas do, in hindsight, it's sort of clear how that could have worked. But at that time, before, it was not very clear that it even made sense, that it was even a thing. And the reason this has become so important, potentially from the viewpoint of applications, again, on Wall Street, a bunch of things are dealt with, you formalize them around stochastic differential equations. These are differential equations where you throw in some random noise. Prices move up and down based on large part, there is some quote noise in the system. So now we are in the conceptual position of having single architectures where you can combine differential operators with standard, feed-forward and attention-based architectures and so on that lie in deep neural networks. Fascinating new direction in which high-level notions of computing, but based on neural architecture, can go. Nishant Lam, it's not just GS. I think there is a lot of, hedge funds don't talk too much about the work that they do in this space. But what I'm talking about is sort of very obvious. There are tons of documents. Documents have tons of information. If we can extract that, it's not about sentiments. It's not about low-level stuff like this. It's about actually financial governance. I showed you formulas. If you can systematically extract the formulas that are embedded in these documents and use that to get a picture of where this loan is, how close to default it is, based on other current information you've got. That's a huge win. If you can use information out in the real world about events that are actually happening to better inform some trading algorithm, that's a huge win. There are lots of potential applications of these ideas all across this board, financial and other domains. Of course, I cannot get into any specifics. Okay. Let's see. Maitri, is there a favorite question of yours you would like me to answer that's come up here?
Favorite? I think one question I did find interesting from the chat is Travis, who asked, where do you see AI being used where it's not the right tool?
There are roaring debates around stuff. And let me just say this. We are in a framework now where code can have very important ramifications for society as a whole. I've been saying this for a while, and this is actually not just tied to AI. It's tied to the massive penetration of computation and networked software into existing life across the globe. The political system in the United States was upended with major upheaval in the last in the 2016 election, mainly because of social media, which is nothing else but networked software that's in the pocket of every human on this planet. Now, there are tons, we're already seeing this. There are huge challenges in the political system. What the heck does this mean? Should a 40-year-old who owns a company responsible only to that board be responsible for laying down the constitution, laying down the rules of engagement, what people can say and cannot say on his platform, because he built the software, he owns the company? Is that what political discourse, civic participation, is that where it is? So it is where it is, unfortunately. Facebook has what is called a Supreme Court, which decides what speech is legal, so to speak, legal as far as Facebook is concerned on its platform or not. There's that question. There are questions of the use of AI, these sorts of things in war making. There are questions about face recognition software. The questions about what ethical behavior should be built into autonomous vehicles, driving vehicles, stuff like this. Now that this has penetrated computer science and AI has penetrated all aspects of human life, it's become a huge issue about working out the right governance frameworks, risk frameworks, constitutional frameworks, accountability frameworks for stuff like this.
Absolutely. I think another question somewhat related to that, but maybe not quite, is the most recent one. Do you think the problem of consciousness will be solved by AI in the next 50 years? Or at least will it be superhuman or solve the RGB problem, in your words?
I'm not going to touch it because all my predictions so far have been complete failures. When the Jeopardy stuff was happening at IBM Research, that crew was developing it. I was in a little bit of competition. My proposal was in front of the same VP as the proposal from this group, Ferrucci and team, to do that. That's not going to work. How could that possibly work? Come on, right? That was my attitude. So that didn't work at all for me. I used to humorously say before Demis Hassabis's answer to how he's going to solve problems like the problem you just asked is, I will solve cancer, I will solve whatever, finance, Jeopardy, whatever, by solving, I'll solve any problem X by solving intelligence, and then that will solve X. What a grandiose answer. What an amazing answer. Except that, while his team is showing, DeepMind is showing tremendous progress on that vision, like the AlphaGo work, like the protein folding work, and so on. So what do we have? We have, like I showed you in my circle slides, we have huge challenges to accomplish. What we are also seeing is technology being applied by a massive number of humans, by the way. Just look at the demographics. 80% of all engineers, all scientists who have ever lived in the history of this darn universe are alive today. And 80% of them are doing deep learning. So the amount of output in deep learning is just tremendous. So it's very hard to predict how exponentials will work out. Nevertheless, there remain huge challenges. So we'll just see, just an exciting time. I can't really say more than this.
No, absolutely.
Jason, I'm really sorry. I don't think, I know of no technology that could help. I'm really sorry.
Well, with that, do you guys have any more questions? I don't see any more questions coming in from the chat. But one question, this is perhaps just more related based on experience, but if there was, this is just out of my personal curiosity, honestly, but if there's like one kind of specific advice you could give our hackers today, or even just those interested in this field, do you have something that might
Absolutely
fall on that line?
Absolutely. Eat your vegetables, do your math, understand statistics, understand probability. This is the heart of what you've got to do in the future. I mean, you can hack all the way you want, but the space of possibilities here is so immense. Unless you have a good understanding of the underlying mathematical foundations, you're going to get lost pretty soon.
Eat your vegetables. I need to do that more. But, and I think before we wrap up, we just have one more question. We have a participant asking, is there any research work to transform code into natural language?
Yes, so a bunch of folks are now, in fact, the reason I changed my field in 2016 to come back to deep learning, come back to AI, was because I felt that proper synthesis of computer science 1.0 and 2.0 might make a big difference. And one of the areas that could make a big difference is the study of programming languages and the analysis and study of code in conventional languages. Now there are a number of research groups that have produced stuff in the space of programs, in particular in the space of recommending what's the next line of code you should write. At some level, code is sequence just like natural language. You've got such tremendous advances in natural language. We now have hundreds of millions of lines of code. If that is available for analysis in the same way that natural language text corpora are available, there's potential that high-level patterns can be learned. And folks are pursuing this for AI reinforcement learning, for testing software, for prediction, for predicting bugs. Tons of applications possible. The specific question was around code into natural language paragraph. Well, it's interesting. Of course, it would be ideal. We are looking at some trading software for which we need to establish that it satisfies some high-level properties. I mentioned this earlier, such as, there are no jumps in the queue. And it would be fantastic to get to a place where code could do that. Look at some source code and come out with a natural language description of the properties that that code satisfies. Lots of research to do before we can get there.
But with that said, I think those are all the questions that we have. Thank you again so much for taking your time out to speak to us about all of this. I'm sure participants learned a lot, as well as taking your experiences and advice to heart. So thank you again so much, as well, for answering the questions. But with that, and all right, thank you. I'm going to go ahead, guys, and share my screen again one last time. We have a couple of quick final announcements. Please see the screen. All right.
All right. Sorry, Took, but we're almost done, guys. So just stay still. I definitely learned a lot from that presentation. So thank you, Dr. Saraswat, for making that. That basically summed up, almost like all my classes that I've taken for the past 5 years. So it's a lot of cool stuff that I learned. So yeah, and honestly, guys, like, don't fret. Even if you don't know what just happened or what was going on, if you just take a first step in this field, I promise you, you're going to learn a lot. So just don't fear yet. All right. We're almost there. We can reach the finish line together. So code of conduct. So I'm going to get a little bit more serious now. This is a safe space for everyone. We definitely want to be respectful, be kind, even if we're not in person, right? We will not tolerate any kind of, bad behavior. And by the way, if anyone or anything makes you uncomfortable at the HackAI event, please reach out to organizers or contact us by our email. When you guys signed up, you agreed to follow the code of conduct. So this is something that we want everyone to abide by at all times. Just be respectful, be kind, and be UT Dallas comments. All right, so that's that. All right, and to wrap it up, happy hacking, guys. It's 12:16. I know we went a little overboard, but right now networking is happening. So if you want to join and just meet other hackers and chill and just make teams, go for it. Or hacking's already started, so you can start IDing projects. Have fun. And let me hear in the chat one more time if you on that hype train. All right. So I'm going to release you guys. Have fun. And by the way, for the sessions and workshops, we're going to fix the bug on Hopin, so you'll be able to see it on the sessions tabs. Thank you guys so much for coming out to this opening ceremony. And we hope you stick around and learn something new. All right. Thank you so much, guys.
All right, thank you guys. Best of luck.